Okay, let's go back to the class. Now will be the last portion of this support vector machine, and maybe I suspect maybe we cannot finish it, but let's just continue, okay, as much as we can. So now we are recording. So we are saying that I share my screen. Okay, so we are saying that now do you have a vector of let's write down that one based on W. Okay, so we have a vector of yeah, this one W times this is the one W times x1. So that is the function. So now you want to take the derivative of this with respect to the change on W, and so now if you take the derivative of this with respect to the change in W is what? Hello? You will be remaining with xi. Okay? So if you take the derivative with respect to W, we will be remaining with xi. So that is the term there. Okay? I was just answering the question of how they come out with this gradient. Okay? So we'll come out with this gradient by taking the derivative of this function with respect to W, because we are looking at how the W will change. Okay? So now, based on this function f of xi, we are computing, we're taking derivative of f of xi with respect to W. And so if we do that, then you will remain with xi. And then what about the sign of, where does the sign come from? Okay, I don't want to go through the details, but the sign is there because of the offset, or because of this one. Okay, I think. Okay, I may be wrong. Okay, or it could be with regard to the classification where you have a sign. mm, It could be with respect to the classification of positive and negative classification. But anyway, okay, we consider, okay, for now, let's accept it as true that you're definitely, it is about the derivative of the function of f of x, where with respect to W, we're remaining with the W, and there is this information about the sign of f of xi. Okay, so the sign of f of xi is the classification of the positive and negative. Yeah, so how it is being, how is it coming at from here? I don't know why it is being included, but maybe they were, okay, the classification because it's not given exactly what is the objective function on the gradient design. Okay, anyway, so I mean, what is it? What's the real function that they are trying to take the derivative with? Maybe there's some other function. Maybe there's a sine function. But anyway, so let's take it as it is, because this is not this is just to say that you're taking the derivative of the gradient. I mean, taking the gradient and then use that gradient the same way as we use our gradient descent method in order to update your W. Okay, that is for the perceptron. But the perceptron, the problem with perceptron is the simpler version of neural network. Yeah. So somehow we can say that they are overlapping. Yeah. So in this case here, how is the perceptron related to support vector machine, or how is neural network related to support vector machine? So for example, in this case, you have this one that we want to, on the perceptron equation, we want to know what is the W that will separate our data from correctly separate our given data. For example, we say in the perceptron, there is that initially maybe you will have your initial W here. Okay, the line separating here based on the W that was given to you is in this case, yeah, that when you draw it in the plane will look like that. But because one is not properly classified, then the next time it will adjust in order to include this one, and so it will draw the next line here. But then again, there are others that are not, then it will draw another line like that, and then it will now that it will stop when everything is correctly classified already. Okay, that's the idea of the perceptron. Okay, so here it will stop once. Okay, maybe there are other lines here like that, and then lines like that, and then until it will stop when, in this case, they are correctly classified already. Okay, so yeah, so here this is the perceptron where your line correctly classifies all the red circles against the blue dots. Okay, so now for the support vector machine, it doesn't stop there. Okay, so it will look for the not just classifying them correctly, okay, where the perceptron stops. For example, this case, perceptron is satisfied already. This case, of course, perceptron is not satisfied because it's not properly classified. This one, perceptron will classify. I will stop, yes, and this one, perceptron will stop. But for support vector machine, it doesn't stop there. Okay. Why? Why? Because because of the many possibilities of the lines that will separate them. So that means that okay, let's concentrate. Let's concentrate in this one. There are many lines. That line, that line, that line still separates. This one separates. So in the case of support vector machine, it goes further to say to choose which line is the one that is correct, that is not correct. I mean, it's not about correctness, but the line that is most optimal in terms of separating the two data. I mean, the two variables of the data. Okay. So how is that being done? So this is the case. Yeah. So now you have circles, red circles and blue circles that you want to separate. Okay. For support vector machine, there is something called we call a support vector. Okay, let's see that one first. Support vectors are vectors that are at the edge of the separation. Okay, so these two here are support vectors of the blue classification, and here are support vectors of the red classification. Again, we are using the linear equation of W2x plus B, or WX, where B can be included here. So in this case here, this line that separates is equal to 0. In the support vectors, the value of this line is equal to 1. If the vector is here, you compute this one is equal to 1. And then again, if the data is here, the point is here, and lying in this line, we compute the value is equal to -1. Okay? And farther down below, the values of these, when you compute the linear function, the values of these points is -1. And then up here, if you compute that function, the value is +1. Okay? So ignore this first. We will consider this later. But now we say that there is this W. The width of this is W. Okay? The width of this margin, we call it a margin. Okay? This is a margin. Okay? And we say that the bigger the margin, the better classification. So therefore, in support vector machine, it is trying to find a margin that is the largest margin possible that separates the two data. Okay. Okay. Well, sir, where is the other margin? Is there another margin that can possibly say that is a smaller margin? Yes, there's a smaller margin. For example, here, I will draw a line here. Okay, and draw a line here. Okay, so in this case here, the margin is small, but still the data are separated properly. Okay, so now when you're trying to solve for the W, it is not just about the correct classification, but then it is about increasing this margin. Okay, so we need to know what is the function, what is it in that margin, so that we can try to maximize it. Okay, so what is in that margin? So we say that we optimize SVM. Okay, not just you. How do we choose the W so that we can optimize the classification of SVM? Okay, so again, this is WT plus B is equal to 0 when you're in the line, and then we can classify. We can multiply it with a variable C. It doesn't change the value. Okay, so we define the. Okay, just go through there, and then we say that the margin is given. We choose a normalization that in this case a WT plus X, where X plus is the one that is X plus is the X that is in the positive vector, positive support vector that is in the positive direction. Where is X plus? It's not shown here. And X negative are the support vectors in the negative direction. So here, these are X negative and there's are X positive. It's not shown in this. Okay, anyway, then the margin is given as this. So the W divided by the norm of W. Okay, so a derivation of this, which I won't discuss in class, but let's just see how they come out based on this equation, how they come out with 2 over the norm of W. So the W, the vector W divided by its norm multiplied that product with the difference of the positive and the negative vector, or the positive and negative support vectors. Okay, so this is the distance between the support vectors. Okay, the dot product of looking at the the biggest. When you say dot product, when you say dot product, what is the information that we can derive from the dot product between two vectors, for example? Okay, the dot product between two. Do you know? Okay, the nice thing about support vector machine is that it is based on simple ideas, but then it becomes, as you put more information to it, it becomes a little more complicated and more complicated. But then, it is easier to understand because it's based on simple principles. Okay, that's the nice thing about very powerful tools. And SVM classification is one of the best classifications among machine learning tools. Okay, anyway, so A dot B, for example, what do you get there? Norm of A norm of B times cosine of theta. Okay, so we say that we can increase uh, support vectors. Okay, it is based on, if this was the support vector, the difference between your support vectors. Okay, and this is the weights, W, the vector of the weights. And so we say that if there's the largest angle, okay, and this is the largest value, or this cosine theta, the largest angle between the two vectors. Okay, A is of course is their norm value, and B is the norm of the B of the other vector. But then given that if these two vectors are the same, or we are using the same weights, and your two vectors the support vectors are you're using the same support vectors, then you can, okay, then you can try to maximize, you can try to choose to see what is the angle in between them. And this angle, okay, this is the only variable that is changing, okay, with respect to this one. So it, given a smaller angles, okay, not beyond 90 degrees, okay. So you can say the bigger the angle, is that correct? The bigger the cosine. Hello. Between 90 and 0, okay. Between 90 and 0, the bigger the angle, the smaller the cosine. Okay. But anyway, the dot product of this gives you some value of how the two vectors are related to each other. Okay. It gives you the angle between the two vectors. Okay. Uh, and we say that the bigger the angle, or the bigger the value, okay, the bigger the value of the dot product is the one that we want. Okay. So now we say we want to know then what is this dot product. Okay. The dot product of the difference of the support vectors. Okay. And the norm, the weight W divided by this is normalized W. Yeah. So we take the normalized W multiplied by the support vectors. Okay. The difference of the support vectors. So now we just write it down. Okay, we take out the dot product, make it as a transpose, the simple multiplication now. And so you take this one. What is this? The support vector, positive support vector minus the negative support, minus the support vector on the negative side. And what is that? Okay. Uh, let's go on the negative side. So there's the solution here. So the negative support vector, okay, this is -1. Okay, the result of that function is -1, and this is +1. And so we go, if we go here, okay, this is 1 minus -1. What is that? What is this? Okay. Wait, where is the annotation? Okay. Now, this is WT times X of the support vector on the positive side minus WT times X of the support vector on the negative side. Okay, so the result of this, okay, this is including the W, this is including the weights, the B, the bias already. Okay, so that means this is +1. Okay, this is 1. Okay, and then this one is based on this one, that's -1. Okay, so -1. So now we say minus +1 because we multiply that one and also multiply +1 -1, and so that becomes 2. 2 divided by the norm of W. Okay, so now this is the one that we're considering. To increase the margin, we need to increase the norm of W. Okay, is that correct? Okay, so this is our objective function. So now this is the margin. The margin, it will be 2 over the norm of W. Okay, so this margin, to increase it, how do we do that? So it is therefore it's the other way around. We need to decrease the weights of the W in order to increase the margin. Okay, so again, you have because this is the now we to decrease, we need to minimize W in order to increase the margin, because 2 over the norm of W. We need to minimize the norm of W. Okay. So now we are given this support vectors, that's equation -1, support vector, that's equation 1, and this is function, the equation is 0. Okay. Again, just to emphasize, then here, if you compute the equation, is -1, less than, because they're away from the margin, from the support vectors, is away from the support vectors, this is greater than 1. In this case, it's a linear separable data, but then because uh, there are many possibilities of increasing this margin, we want to choose the margin, we want to choose the classification with the biggest margin, where the margin is stated as 2 over the norm of the weights W. Okay, so we want to maximize 2 over W. That means we want to minimize W, yeah, equivalently this one, and subject to here x1 plus b greater than 1. Okay, we mentioned this one already, that here is greater than 1 multiplied by yi is always greater than 1. Here less than 1 multiplied by yi is becomes greater than 1. So we can multiply this all together to make it greater than 1 for all I from 1 to n. And so now we have a simplified, we had a simplified objective function now based on the W alone. So we want to minimize the norm of W instead of maximizing 2 over W, minimize the norm of W subject to this condition. Okay, and this is called quadratic optimization problem. Okay, just want to show you how things are, 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 are derived. Okay, so now, for example, this, but then for example, in SVM optimization, it could be that here, this is the best classification, okay? Because it correctly classifies all these, okay? None was wrongly classified. But sometimes, the second picture can be a better classification, okay? Well, because the margin is big, a big margin there, but yeah, there's one misclassified, it could be okay. Yeah, rather than here the margin is very small for classification, and then there's no misclassified one. Okay, sometimes this second picture can be better because maybe, okay, maybe just one misclassification is okay, because if for unseen data, maybe this one will classification here will work better than this one. Okay, maybe if increase the data here, that will be more here blue, more here red, and then you want to do here, you have more blue, blue will be coming out here, so you have many misclassified data already. Yeah, because you didn't do this because you are scared to misclassify this one. Okay, so sometimes a little bit of trade-off between accuracy can of the current data can increase your classification for unseen data, classification accuracy for unseen data. Okay, so yeah, in some point there can be misclassified data. For example, this point can be is misclassified, but you maintain the margin because this is the largest margin. Yeah, there can be a classification violation that is okay. Okay, it can be a trade-off. So now let's go back to optimization. So now we say that here we assign a psi 0, which is a value that is between 0 and 1, that the point between the margin and the correct side of the hyperplane, where in this case here is when you are in the hyperplane is the one that separates this one. So we just assign a psi greater than 1, a psi equal greater than 1 when it is misclassified, okay, and psi equal to 0 when it is classified correctly. Okay, so in this case here, this is psi greater than equal to 0 because it's classified correctly. Here, this is not classified correctly. I mean, it's still classified correctly, but it's inside the margin. And so we say that this value is less than, is less than 1 over the norm of W. Now, as you go further in, becoming misclassified, now this is great. This one will become larger. Okay. Anyway, these are the psi will be used for optimization later. And so now, therefore, our psi is needed to be minimized. Okay. In fact, we want it to be zero so that it will become a correct classification. Okay. So as you go further inside, the psi will increase and increase. Okay. So even if you go here, it's increasing already. Somehow it's greater than zero. Okay. And now it becomes much greater as you go further. So therefore, we want your psi to be minimized as well, together with your W, subject to this one. So we want to introduce the psi, okay, because it will help us in classification, which you can see later. Okay, now these are all. I don't want you to go through all uh, details, but I just want you to have some overview, understanding on what's going on regarding optimization of support vector machine, or SVM. Okay, so we we are saying that this is the objective function, or the one that we want to minimize. Minimize the norm of W, minimize the psi, subject to this constraint. Okay, which in this case we can write in one optimization function, including the constraint. So now we can say minimize of W, norm of W, and including the addition of which one is greater. Yeah, 0 or 1 minus this one. So in this case, maximum, it says here, you choose the maximum, whether 0 or this one. That means you only take the positive value. Okay. So if this becomes negative, you take 0. And this, if this is positive, you take this value. That is what it is trying to say here. And you take, and then you add all those for all data I. Okay, so this is the loss function, and this is regularization. Anyway, so those are the terms. Just bear in mind that there are two things that we want to minimize: this function, which is not continuous, and this function, which is the norm of W. Okay, so now we have the loss function. Okay, so we say that because of this loss function, because of this function here, we have a hinge loss. Yeah, it's like a hinge. It is not continuous. Okay, I want you to understand this part here, that because of the hinge function, the objective function for SVM optimization becomes discontinuous, and so because of that we cannot differentiate. Okay, so in this case here, we want to differentiate. When you're given with objective function, that is the objective function that we want to differentiate, so that we can use that in the gradient, as a gradient to correct the weights. Okay, so now if you take the derivative of this, okay, this convict function, anyway, those are, okay, this is the function that we want to take the derivative, but it is not continuous. Okay, convex function, meaning never mind, but this is a convex function. Okay, so what we want to do is actually like this, the same thing as what we did before. So as you can see, all these things are repeating. Okay, so we're again computing for the weights. Yeah, initiating the weights and correcting it based on the gradient. Is the gradient. This is just the learning rate, and this is the gradient. We keep seeing this value. Okay, so now what then? What is this value then? Okay, so the point here is that this gradient, okay, will depend on the objective function that you define. Okay, so now SVM defines a certain objective function. Okay, our polynomial regression has different objective function that we take the gradient like that, and some other things that we take the gradient with. Yeah, we take the gradient because we want to optimize our W. So when you say the gradient will be based on what you are trying to optimize. So for example, in our linear regression, it is the error. We want to minimize the error, and we take the gradient of the error, so that when you compute your W, you get the W that is already optimized based on your objective of minimizing the error. But in this case, in SVM, I'm running out of time. Okay, let me just finish the time until this one will cut us off, and then we'll continue next meeting. So you minimize this function norm of W against this discontinuous function. Okay, so because this is not a continuous function, we cannot take the gradient immediately. Okay, so this is not differentiable, and so we say we take the subgradient. Okay, instead of saying the gradient descent, taking the gradient of this function we cannot take because it is not continuous, and so we take the subgradient. Okay, okay, let's skip this one. Okay, so now, okay, by taking the subgradient, okay, so we take the derivative of this. Okay, and so the result is take the gradient of this, and you define it as the L function here, where this is the L function, this is the discontinuous function or the hinge function. Okay, so because this one, you take the derivative of that, this one cannot be differentiated, you can also differentiate this, and you take the gradient of that, and so the result is this. So you just take the derivative of this function. Instead, you take the derivative of that, okay, of this function, rather than taking the derivative of this discontinuous function. Okay, so now it becomes a lot simpler now. So now you say that this is the equation. Okay, so again, if this one, if f of xi is less than 0, you take this, otherwise you take this. So there are two functions. Okay, so because of the discontinuity. Okay, so now, yeah, these are the weights. So this is the initial weight, this is the current weight, this is the current weight, this is the weight value, this is the data, and this is the classification. Okay, if this function is less than 1, otherwise you use this. Okay, so what does it mean when this function is less than 1? When it is misclassified, because it's always greater than 0. If it's greater than 0, then we compute this, that the things are classified correctly, and then all we need to do is compute for W that will maximize the margin. Okay, so these are the equation of SVM optimization. Okay, so now, again, it's easy because it is based on the same principle as before. We don't need to derive that. All we need to do, we don't need to make all the derivations in the examination. All we need to do is just make sure that we apply the equations, SVM equations, correctly, and then we initialize the weights, and then we given certain data, and then we classify them, and then come out with we run this iterative algorithm to look for the weights. Once we come out with that weight, we say we stop a certain number of iterations, then we, given new data, we'll check if we classify them correctly. Okay, is that understandable? Okay, it will be more understandable together with the laboratory. Now we have new information. Now I will give you a laboratory exercise for the support vector machine. So that means next week we'll have laboratory exercise, and then there's another way of computing support vector machine as well. I will discuss it in the next meeting, and it's very short, it's very fast, it's not, it will not take a lot of time. So I will stop here, and then I will discuss the other method next meeting, and then I think we will finish it fast, and then we'll start with neural network. Okay, if please keep your questions now. I will wait for them next meeting because we're running out of time. Okay, let me stop sharing because I want to see who are here. Oh, how many students are left? I'm sure Mr. Oni is not around. See, he's not around. Okay, and what is this? One and Musa. I was thinking Musa was not here, but he is here. Okay. Itumiling is here. Itumiling must be here. Okay. And Mr. Tim, of course, Timana. He will be here. Yeah. Okay. Okay. See you guys next meeting. Yeah. Okay. Thank you for coming today. I will give you an exercise for laboratory. Okay, I will upload it. Okay,
Yeah.
thank you. Bye.
Yes, sir.